few words about solving problems about linear dependence and independence. Everything goes back to vectors in Rn. So let's say that we have some number of vectors, a1 vector, an vector. Note the difference between m and n. The dimension of the vector space and the number of vectors. So the way we write these usually, we use column vectors. It would be equivalent representation to use row vectors, but then we have to choose one and just let's choose column vector representations. So we have these vectors, let's say that with then m components, since it's in Rm, and then we have n of these vectors. Then for linear dependence and linear independence, we want to look at their linear combinations of the list a1, am. This is with scalar coefficients. So you can have many different notations for these scalar coefficients, but because we want to work with linear systems, it's convenient to use x1, xn. So these are scalars, these are real numbers. So linear combination means we multiply the vectors with scalars and then add them together. Very important, this has an equivalent formulation, these scalar combinations of these vectors. We can collect together the column vectors into a matrix and then these x vectors into a vector, column vector. And then according to the rules of multiplying the vector and the matrix, this is the same. Then what we have here is a n by n matrix. The column vector can be considered as a n by n vector. So when you multiply together two vectors, these dimensions next to each other must match in order for the multiplication to make sense. So yes, it makes sense, n equals n, and then the result is a n by n vector. Let's say that we denote this with b1, and altogether we have m rows. So this is m, b1, bm. Again, please notice the dimensions, you should be comfortable with them. So we have n vector here, and then we get an m vector after multiplication. Okay, so we can call this ax equals to b linear system. Special case, if we have x1, a1 plus xn, an, linear combination results in the zero vector. The way we can write this as a matrix vector equation is then that ax equals to 0. This is called homogeneous linear system. Note, x1, xn equals 0 is always a solution. This is called a trivial solution. And also then the corresponding linear combination 0a1 plus 0an is 0, and this is called a trivial linear combination. So then here is the definition of linear independence or linear dependence. If only trivial solution exists, then the list a1, an is called linearly independent. And then if non-trivial solution exists, or first let me mention then that x equals to 0 in this case. So then if x equals to 0 is the only solution, then linearly independent list. And then the second case, if non-trivial, that means x is different from 0, solution exists, then a1, an vectors, or the list of them, is called linearly dependent. And then we have the cases that if x solves the homogeneous linear system, then any scalar multiple cx also solves it. That's because if you substitute x with cx, the scalar multiplication can be brought to the front, and that results in c multiplying the 0 vector, which is the 0 vector. Then if x1, x2 are two solutions, so they solve the homogeneous linear system, ax equals to 0, then their sum, x1 plus x2, also solves it. We just have to check a times x1 plus x2 equals ax1 plus ax2, and that's then 0 plus 0 according to the rules of matrix vector multiplication. You can distribute the matrix multiplication through the vector addition, and then this results in the 0 vector. So because of that, because of this scalar multiplication and the vector addition keeps solution, we get a whole subspace of solutions, starting with the set of 0 vector when only the 0 is a solution, or if it's not just the 0 solution, once we have one solution, then any multiple is a solution, so we get infinitely many whole subspace. That might mean either the 0 vector alone, which is just one vector, or infinitely many solutions. So then we have the dimension of the subspace could be then 1, 2, and so on. And then the maximum dimension is, of course, the whole space. The whole space was M. Because of this description, the whole idea of figuring out whether a list of vectors is linearly dependent or independent is about solving a linear system. So first of all, solving in general a linear system ax equals b, what we do is we have an augmented matrix, and then we do Gauss-Jordan elimination. Now, we only need a special case when we have a 0 right-hand side vector, ax equals to 0. So in this case, the augmented matrix would be the last column, the 0 column. And when we do the Gauss-Jordan elimination, we do row operations, adding together scalar multiples of rows. The 0 column stays 0, and because of that, it's really not necessary to carry around. But at some point at the end, in the last step, we should remember that what it means when we have a Gauss-Jordan elimination for the A matrix. It's not a mistake to carry it around, it's just I'm not going to do it because it's not necessary. And the Gauss-Jordan elimination is that we transform the matrix into a so-called reduced row echelon form, where we have in the matrix at the end, we have leading ones in the rows, and then above them we're supposed to have 0, and under them we're supposed to have 0. These are called the pivot elements. These are not necessarily diagonal matrices. So the diagonal matrix would be the unit matrix, the identity matrix, where only the diagonal entity has 1s and everything else is 0. So we have other possibilities. for the reduced row echelon form. We can have things like 1 here, and then some other entry star, but under the pivot we must have 0, and then maybe in the second row, in the 2-2 entry, we don't have a pivot. We might have the pivot, the leading non-zero entry, in the third place. Above this we must have 0, and under it we must have zeros. And then whatever we can have. I want to concentrate on this part now, where we have a column that doesn't have a pivot, because it's not the leading term that we have here in the position of star. So this the first column corresponds to x1, the second one x2, and the third one to x3. So now what we have is, if this is the situation that there is no pivot in a column, this x2 is called a free variable, and this automatically results in infinitely many solutions. We can also have a situation like it looks like a diagonal first, but then we have, in addition to the 3 rows and the 3 columns, we have a 4th column with some entries. It doesn't matter what those entries could be, 0, doesn't matter. So this is not a diagonal matrix either, because it's not even a square matrix. So in this case, this is also a free variable, no matter what those numbers are. That's right now it's x4, the column, the 4th column. Again, we have infinitely many solutions, and they are non-zero. For example, this is always the case, or something like this always comes up. In this case, this is 3 component vectors, but we have 4 of them. So what we have here is 4 vectors in R3. We have more vectors than the dimension. That means, since we have infinitely many non-zero solutions, that means non-trivial linear combinations that equals to the 0 vector. That means the column vectors are linearly dependent. And we have a theorem about this. Let me remind you to go back to your notes and look up the theorem. So let me show an example. We have 1, 2, 3 vector, 2, 0, minus 5 vector, 2, 5, 4 vector, and the 4th vector, minus 7, minus 19, minus 11. The question whether or not the list of these 4 vectors is linearly dependent or independent. So first of all, these are 4 vectors in R3. 4 is larger than 3. That means we know for sure that this will be linearly dependent list of vectors. So this part is easy to answer, but then what requires a significant amount of work is how to get a non-trivial linear combination. That means you want to find coefficients x1, x2, x3, x4. And the way we solve this is that we put together the column vectors into a matrix. 1, 2, 3, 2, 0, minus 5, 2, 5, 4, minus 7, minus 19, minus 11. Then we have the x vector that's supposed to be equal to the 0 vector, and we want to solve this for x. These will be the coefficients in the linear combination. And of course we want to solve for x which is not 0. Again, 0 is always a solution, but we are not interested in the trivial solution. Because of the 0 homogeneous linear system, we do not augment the matrix, or at least there is no need for it. So what we do is a Gauss-Jordan elimination. We want to make entries under the 1, 1 entry 0. So let me write down the steps. To make this 2, 0, what we do is the new row 2 will be row 2 minus 2 row 1. So we get 0 here, minus 2, that's 4, minus 4 plus 5, 1, and then minus 2 times minus 7 is 14, minus 19 is minus 5. Then the new row 3, in order to create 3, we multiply the first with minus 3, so this will be row 3, minus 3, row 1. Again we get 0, minus 6, minus 5, minus 11, minus 3 times 2, minus 6, plus 4 is minus 2, minus 3, we have plus 21, minus 11 is 10. So we are done with the first column. Then we continue with the second row. We find the first non-zero entry and we start making things under it 0. Now, here is a very important technical step. Most homework assignments, not just in web work, but in pretty much all textbooks, the solutions are typically integers, nice solutions. It's always possible to avoid fractions in this Gauss-Jordan elimination. Nobody likes to work with fractions on paper. I don't like it either, so that's a very important trick. What we have to do is we have to use least common multiples. Also, make pivots 1 only at the end. So don't start dividing to force the pivot entries 1. And if that bothers you, this trick, this actually works not just in the homework assignment with integers, but sometimes people do that in computational mathematics as well, because even in computers there is problem with fractions, since they introduce finite digit arithmetic, rounding errors, and there is so-called scaling of matrices and entries to ensure that you don't end up dividing by a small number and get a huge number and you get overflow. So what we do now, we start with the second row in the next step. We don't do anything to that, but now we make the entries above this minus 4 and below it 0. How can you make 2 equal to 0 using minus 4 without doing any division? So the new row 1, if I multiply it with 2, I get 4 there, and then I just have to add row 2 to it. So I get 2 there, and don't worry, we will take care of this scaling so that it goes back to 1 later. Then the 220 we multiply by 2, we get 4, minus 4 is 0. Multiply the third entry, 4 plus 1 is 5. 2 times minus 7, minus 14, minus 5 is minus 19. No fractions. Then to get row 3 from minus 4 and minus 11, I multiply the third one with 4. Then I get minus 44 there, and then to cancel it I have to multiply minus 4 with minus 11. So what I get here is minus 44 minus 11 times minus 4, and that gives me 0. Again, no fractions. Notice that this entry doesn't change, the one entry in the third row, since we are working with zeros already there. It's a little bit tedious now to keep track of what we are multiplying with what. So 4R3, that's minus 8, and minus 11 row 2, that's minus 11, so this is minus 19. Then to get this entry, 4 times R3, so this is 40, minus 5 times minus 11 is plus 55. So this is now 95. All right, so then I still don't want to divide because, to get ones in the pivots, because right now if I divide by 2 to get 1 here, I would get 5 over 2 That's not good. Also, I will get -4. To get 1 here, would have to divide by -4, and then I would get 1 over -4, which is not a nice number to carry around. So then I got to the last row, to the last pivot. The first non-zero entry in the last row is this pivot entry then. Now, once we are in the last pivot row, it is time to divide, because this row doesn't change anymore. We are now going backward once we reach the last row. So time to divide before going back up. So I want to make this pivot 1. That means that I'm gonna divide third row with -19. So I get 0, 0, 1, and this is miraculously it's integer -5 there, because it's a homework assignment and we have nice numbers for the homework assignment. So now we go backward up, and we make these entries 0. For row 2, all we have to do is subtract 1 from 1 to get 0. So this is row 2 minus row 3. And then for row 1, what I have to do is subtract from row 1 5 row 3. We're supposed to use the pivot row. So the row 1, 2, 0, 0, because we are making it 0. Then -5 row 3, so this is 25, -19, that's 6. Then, so actually this is where I'm going actually with this row manipulation. Second row, 0, -4 do not change. This is 0. I'm subtracting -5 from -5. I get 0. And then the last row doesn't change anymore. Everything under the pivots and above the pivots, 0. The only thing missing is now to make all the pivots 1. So I do have to divide the first row with 2, 1, 0, 0, 3. Second row with -4. And the third row just stays there. And because now I'm finished with the Gauss-Jordan elimination, at least the writing of the process to reducing it to row echelon form, now I want to emphasize this is a part of a homogeneous linear system. And again, this is in reduced row echelon form. You cannot reduce it anymore. This is the best form you can get. Ones in the pivot entries 0 above and under them. In this column there is no pivot, so 1, 2, 3, 4, x4 is free variable, and this already shows that there will be infinitely many non-zero solutions, so that means the linearly dependent system that we have here. And then to solve the linear system, you now want to write that this is x1, x2, x3, x4 columns, and write it as a linear system. So the first row represents x1 plus 3x4 equals 0. And then you can solve this for x1, I'm sorry. The point is to solve for the pivot variable. So this is minus 3x4, while x4 is free. Then the second row, x2 equals to 0, there is nothing to solve there. And then the third one, x3 minus 5x4 is 0, and we get x3 equals 5x4 as a solution. And for example, if in WebWork it wants some specific numbers for the linear combinations, then you can choose a nice number, for example, x4 equals to 1. You shouldn't choose 0, but because then you get a trivial solution 0, 0, 0. So other nice number, which is not 0, is 1. And then what we get is x1 is minus 3, x2 is still 0, x3 is 5. We can also check this, that the linear combination x1 a1 plus x2 a2 plus x3 a3 plus x4 a4 equals, in this case, minus 3, and the vector was column vector 1, 2, 3, plus 0 times 2, 0, minus 5, plus 5 times 2, 5, 4, and x4 is 1, so plus 1 times minus 7, minus 19, minus 11. So minus 3 plus 10 is 7, minus 7 is 0, minus 6 plus 25 is 19, minus 19 is 0, minus 9 plus 20 is 11, and minus 11 is 0. So here we go, we have a non-trivial linear combination of the vectors that creates the 0 vector. Let me remind you that if we have polynomials, for example, we have 3 plus 4x minus x cubed, you can write this as 3 plus 4x plus 0x squared minus 1x cubed, writing out all the powers of x in increasing order, and then you can create a vector just collecting the coefficients 3, 4, 0, minus 1. So then we are working in R4 with 4 vectors. So this trick makes us possible to use Gauss-Jordan elimination and solving linear systems even if we work with polynomials. Or for example, if we have matrices, a matrix like 9, 0, minus 1, 2, it doesn't matter what order you choose, just follow the same order. For example, row by row, collecting the coefficients 9, 0, minus 1, 2. Again, we get a 4 vector. So make sure that you keep the same order. And I want to emphasize that it's very, very useful to use this least common multiple rule in order to eliminate entries, numbers in the entries, without working with fractions. Finally, a few remarks how you get linearly independent vectors from Gauss-Jordan elimination. So in that case, for reduced row echelon form, you will get the identity matrix, and then if you have the augmented one with the zeros on the right hand side, then that means that you have to solve x1 equals 0, but actually it's already solved, so it says x1 equals 0 and xn equals 0 from each rows. This is what indicates that you have a linearly independent column vectors. Or it's not necessary to get the identity matrix in this form, because it's possible that you have actually less vectors than rows, but still you're supposed to get at least part of an identity matrix, and then the rest of the rows might be just all zeros, and then the right hand side is 0. So if this is the case, then these last rows do not matter, because they don't give any information. They just say that 0 equals 0, which everybody knows and nobody cares about. And then still the first non-zero rows say the same thing, that the corresponding variables x1 and x2, or maybe more, should be equal to 0, which again indicates linear independence.